In the previous video, we proved the first fundamental theorem of calculus, which states, if f is a continuous function on an interval that contains the number a, and we define the area accumulation function to be the integral from a to x of f of t dt, then the derivative of the area accumulation function happens to be little f of x, the integrand. In this video, we are going to look at how we might use the first fundamental theorem of calculus in order to find the area underneath a particular curve. So what I want to do is I want to start by looking at a general picture. So we're going to have a set of axes, and let's have a function. So here is y is equal to f of x, and we can think about this as the x-axis and this is the y-axis. And I want to have an a value and a b value. So let's get them labeled. There's a, there's b, and I've got this nice chunk of area here underneath the curve. Now I already know that that area can be written as the integral from a to b of f of x dx. Now I also know that the variable of integration is a dummy variable, and so I can rewrite this integral as the integral from a to b of f of t dt, because it really doesn't matter what I call this independent variable's name. Now the question is can I somehow use the first fundamental theorem of calculus to help us figure out a way of getting the area quickly? So the thing that I want to do is I want to remember a couple of things. The first thing is I'm going to recall that from the first fundamental theorem of calculus, if I set a of x equal to the integral between a and x of f of t dt, then I know that the derivative of that area accumulation function is just f of x. Now the other thing is that I'm going to make a note of over here is that if I evaluate the area accumulation function at b, I'm going to get the integral between a and b of f of t dt by the definition of the area accumulation function. But since the variable of integration is a dummy variable, this is also the integral from a to b of f of x dx. In other words, this a of b is going to give me that yellow area that I am trying to find. Now what I want to do is I want to make a new hypothesis. Suppose we know that capital F of x is an antiderivative for little f of x. In other words, we're going to suppose that capital F prime is equal to little f. And what I want to do is I want to see what does that say. Now it's important to realize that capital F may or may not be my area accumulation function. But I do know that since capital F prime is equal to little f and capital A prime is also equal to little f, that's enough. F is equal to a of f plus some constant. Now, I can exploit the geometry of what I know to figure out what that constant is. So let's look at this. We know we know that the area accumulation function evaluated at A is the area from A to A of f of t dt. That happens to be, and I just want to look at the picture again, that happens to be the area of this line segment. And areas of line segments are 0. So I know that this guy here is equal to 0. And what does that tell me? That lets me write an equation. That tells me that f of A will be equal to the area accumulation at A plus a constant, but this mess here is known to be 0, so we get f of A is equal to 0 plus c. That says f of A is actually equal to c. And that also tells me that capital F evaluated at x is just going to be the area accumulation function at x plus capital F of A. Now what I want to do is I want to put x is equal to b into this formula. So substitute x equal b. And when we do, we get the following important thing. F of b is equal to, is equal to the area accumulation function at b plus capital F of A. But what does this say? If I want to find the area, I want to solve for this. So if we solve for the area that we are trying to find, we get, subtract this off both sides, subtract f of A off both sides, and we get the area accumulation function at B is going to be capital F of B minus capital F of A. In other words, the integral between A and B of little f of x dx is equal to capital F of B minus capital F of A, where capital F is any antiderivative of little f. And this is such an important fact that it actually winds up being called its own theorem. In other words, what we have now done is we have actually proven the following second fundamental theorem of calculus. If f is a continuous function on the interval from A to B, and capital F is any antiderivative at all for little f, the definite integral is equal to capital F of x evaluated between A and B, which is equal to capital F of B minus capital F of A. Now, if we happen to have a problem where an antiderivative is easy to find, the second fundamental theorem of calculus makes it easy to find the area. And I want to end this video with an example. So as an example, I'm going to draw an area. And this area is going to look like this. This is the function y is equal to x squared. And I'm going to have a line there. That should be a vertical line. So let me actually delete that line and start over. So I'm going to have a little line here and a little line here. Ooh, let's see, those are not good either. So I'm going to have a little line here and a little line here. And this line is going to be at x is equal to 1, and this will be at x is equal to 4, and I want to find this area. So I want to find the integral between 1 and 4 of x squared dx. Now I want to make a note. We already know that an antiderivative of x squared is x cubed plus 3 plus any constant that we want to add, and I'm actually going to just add 0 here. And so what that means is that I can write the definite integral between 1 and 4 of x squared dx. That can be written as x cubed over 3. Evaluate between 1 and 4, and that will be 4 cubed over 3 minus 1 cubed over 3. That will be 64 thirds minus 1 third. That will be 63 thirds. That will simplify to 21.